recording now. So I didn't mention this in another class, like in Russian, there's a word velociped, which literally means fast walking, and that stands for the bicycle. So a long time ago, I mean, the earliest bicycles were like you would be walking, standing and walking, and the wheels would be turning and it would be walking faster. So the origination of the word velociped is veloci, which means fast, speed, and ped means like walking, like pedestrians are walking. So this is how you can relate to this, like bicycle. So I'm making this claim that if we can find the area under the line here, that this area will represent displacement. Again, I'm using not distance, but displacement. And again, the meaning of this will come in a little bit later. So for now, just use these fancy words, and a little bit later you will understand why we're using these words. So let's see. What kind of shape is that? Like in general, what does it look like? You can type the answer. Right, rectangle. All right, rectangle. So for the area of rectangle, we know that the formula is height times base. So we don't care which one is height, which one is base, but we need to clarify one thing. To find, let's call the base as the base, the bottom, right? To find that, we will need to find the difference between T final and T initial. So this will be V, which is right here, times T final minus T initial. Why is it T final minus T initial? Let's say you're observing an event and you're using stopwatch, and then you started the stopwatch, you're watching this, something else happened, and that draws your attention, and you look at it and notice that it started, the second phenomenon, the second thing happened at 45-second marking, and then it stopped at 90 seconds. Can you figure out how much time the second event took place? The answer is yes, right? So from 45 to 90, that's 45 seconds. So you automatically subtract 45 from 90. So that's why we write T final minus T initial, okay? Okay, so that's one formula that relates with velocity, time, and displacement. And I'm sure all of you are familiar with the rate equation, like rate, which is speed and time and then distance. So it's kind of similar to that. Next one. Let's say you are a Formula One driver and you are at the beginning of the race, at the start. They give you, go, and you step on the gas, right? So how would the graph look like as you gain speed every second? Right, okay. So it will look kind of like that, right? So it's like a certain angle going like that. Now, yes, it could be exponential, and then in all honesty, in the real life, probably a lot of them are slightly exponential, because like especially Formula One probably will be exponential, but in a general situation, you don't want to feel that kind of acceleration. Like, roller coaster is fun, but you don't want to like go on roller coaster every day, right? From morning, like you go to school, for example. If you were to go into school from 8 to 3:30, you don't want to be on a roller coaster from 8 to 3:30, obviously, right? Because it has all kinds of crazy accelerations and they're changing all the time. And even in the car or in the bus or whatever, you don't want to experience this kind of thing because this is unusual, and we like when we can predict motion. And if we're experiencing if you're gaining speed at a constant rate, then you can adjust your response to that. your body will be responding with certain forces, and the forces applied to you will be constant. So you will become accustomed to that, and it's easier. If it's like changing exponentially, then it creates a lot of discomfort. And this for the people who like roller coasters or like fighter pilots, that's good for them. But like ordinary people don't like that, experience every day. Okay, so it's gonna be linear graph like that, and then again we're gonna try to find the area like that. So in this case, again, the same plane, we say that this area is equal to displacement. And obviously this is a triangle, right? So we can draw that, write the equation, base times height. So here I'm gonna make a little tweak, and a little bit later you will understand why I'm writing it this way. But right now I want you to trust me on this. And I won't say trust me very often. I will actually say do not trust me most of the time. Use your own brain, analyze what I'm saying, see if it makes sense. Sometimes I may be wrong. I'm a human being. I make mistakes. Sometimes I will say purposely wrong things to see if you agree with certain misconceptions, to help me to reveal your misconceptions and then kind of wrestle with them. So do not trust me, okay? But here I want you to trust me just a tiny bit until we get to the next step. My role is not like say to you this is how it is and you believe. My role is to present the reasoning, and your role is try to develop similar reasoning and see if conclusions we draw are connecting with your reasoning, okay, with your rational thinking. And if they're not connecting, then you obviously will come up with questions. If they're connecting, then you will also come up with questions to deepen your understanding. So trust me on this just a tiny bit. So I'm going to write this here. So V final is here. This is V initial, T final. And I'm going to write the equation down below here. So D equals 1/2 V initial plus V final, T final minus T initial. So that's going to be the equation for displacement for the triangular shape. Okay. All right. So in the next step, it will become more clear why it is so. Next situation is you're in the car, you're driving on a service road and about to enter and have to enter the highway. So how would the graph look like? It's like you're moving at 30 miles per hour on the service road, and now you have to accelerate, let's say, to 60 miles per hour on a short, like shoulder, well, not shoulder, what's it called? Ramp, right? So how would this graph look like? Okay, be active, respond. So right now it's okay to respond to everyone. A little bit later I'll ask you to respond privately, so we don't like say it out loud to everyone when I need more like individual inputs. Okay. Horizontal line, then positive slope, probably linear. Okay. Steepest slope. Okay. All right, good. Excellent. So all of you trying to kind of come up with the realistic, right? But we're learning elementary physics. It's for elementary students like you guys. And we have to simplify the picture. So say we forgot to observe this motion and we started observing it a little bit later, and will look like, like that. Linear graph with the non-zero y-intercept. Does it make sense? Right? Somewhere there was 30, and then now it's going to 60. Maybe you didn't get to 60 yet. Who cares? And instead, we're not really involved with numbers. We're doing a little bit of algebra, so who cares? So we're going to draw this thing. Blim, blim, blim. And T, whoa, that was unexpected. T initial, T final, V initial, V final. I draw much better on the board. Trust me on that. Okay. What kind of shape is that? Trapezoid. What kind of trapezoid is that? It's a right trapezoid. Yes. Does a wrong trapezoid exist? If it's the right one? All right. Yes, that's correct. It's a right trapezoid. So if you don't see it, you should turn it on its side, and all of a sudden it becomes trapezoid. Why is it important to identify it? Because we need the area formula. And as far as I remember, it's B1 plus B2 divided by 2 times height, right? So it's a trapezoid. Yeah. Trapezoid. There you go. So basis of this trapezoid will be V1 and V initial, V final, right? So then we can write displacement as 1/2 V initial plus V final times T final minus T initial. So now you should notice that these formulas are essentially the same, right? This one and this one. And there must be underlying reason for that, because it's not a coincidence. Let's try to understand this from we're going to use imagination, right? Physics is like, I think Einstein said something about imagination. So it's like, you don't have to be a mathematical genius, but you gotta have imagination to do well in physics. So stop writing, just imagine, please. So we have this trapezoid, and in our mind we can actually magnify, we can make it as big as we want. We're gonna make this part really long, okay, really long. We're gonna make this base, even though it's a base, I'm gonna call it height, whatever, tall. We're gonna make it really tall, and we're gonna zoom out away from the trapezoid. It grows really big, but we also move away from it, and we forget to increase the size of this base. So what happens? What will you see in your mind if you expand everything with the trapezoid except this base? Responses in the chat. Actively, everybody should, participate. That's the best way to participate. Just type in a couple of words and you get the point. Right. It will become indistinguishable from triangle, right? Because we're using our imagination, this base becomes almost zero, right? We can say, oh, it's a triangle, but if you zoom in, it will look like a trapezoid again. So there you go. This is the shape is the same as this shape. So I'm saying triangle is trapezoid, and trapezoid is triangle. Trapezoid is truncated trapezoid. Trapezoid is truncated triangle. So we cut off part of this and it became trapezoid. But if you don't, then you have a triangle. So thus the formulas for the areas must be the same. In fact, we can go on to say that trapezoid is also a rectangle, where the two bases will be equal, right? If two bases are equal, that becomes a rectangle. So in fact, we can state that this formula essentially is the same as this formula. and then the base here remains constant. It does not change from B1 to B2. Does it all make sense? Yeah, you can nod if you agree. Is it too much for imagination or okay? Okay, all right. So hopefully you will understand that. Now, if we used minus here, like V final minus V initial, then we will end up with a situation then that the formula for the triangle will become wrong. How would you call this quantity when you add two numbers and divide the sum by 2? Yeah, so we have average. Sometimes we call it mean. On the graph, we can call it midpoint, right? So also remember this, mean is like average, right? When someone is mean to you, they want you to be average. So you don't want to be average, you want to be special, right? So keep that in mind. The formulas we're getting here are general, or you can call them mean if you want, because they are going to be correct all the time or most of the time. And then a little bit later, we're going to derive special equations, which will be specifically useful, with problems that we will deal. Well, what is a special? Special. So mean is average, right? When we disregard people's, special talents or whatever, we demean them, we bring them down, and it's like when we appreciate them, people become special to us. So same with formulas, by the way. Let's try this. This formula could be modified now to this. D equals, let me actually correct that. Total displacement equals average velocity. So I'm writing the whole word, but later I'll just write AVE times delta T. So a couple of important points here. I'm going to box this one. And this one. So someone asked about reference table. I don't remember which class. You will not be using reference tables. I forbid you using reference tables. Don't use reference tables. Why? Because those formulas do not belong to you. You didn't come up with those formulas. You didn't develop them. You didn't print. That's not your paper, and it's not yours. So what I want you to develop is ownership of the formulas. And the way to do it is, one, to write it with your hand. So when you wrote it down, it's kind of yours. Two, derive it on your own, right? And then three, put a nice piece of paper and frame it. No, don't frame it. I'm kidding. But do put on a nice piece of paper. So you're going to accumulate formulas, useful formulas. And if you have not prayed yet, you're going to start praying every night before you go to sleep. You can take that nice piece of paper with a few formulas, and it will, the number of formulas will increase. And you will pray every night right before you go to sleep, okay? I don't care what you think about when you look and stare at those formulas. Somehow part of your brain will be thinking and recognizing symbols. And eventually you will remember this formula so well that if I call you at 2 in the morning and ask you what's the equation for uniform accelerated motion, it will be right there. Okay. This way you will own the formulas. They will become yours, hopefully, for a long time. Okay. And this is a practice I've been doing for a long time in class, regular, like, you know, physical classroom, and it works. Okay, those who actually follow these instructions, they do come up with a nice set of formulas in their brain they can use freely without the reference table. Also, once you pray, right, you're gonna put that under your pillow, and overnight the formulas will, like, through osmosis, will go into your brain. So this is another kind of additional step. Okay, it works. So I remember one time I had in college, I had this difficult problem. It was I think some physics course, I don't remember, and I couldn't solve it, and I was so tired, and I just lie down with my head on the book. In my dream, I solved the problem and I wrote down. This happened to me once, and I tried after that many times. It didn't work, but that time, I guess I was so frustrated, it worked. So some osmosis probably, took place there. Okay, so all jokes aside, this is how you own the formulas. You develop them on a blank piece of paper from your hand, right? If you can do it freely, confidently, with confidence, then that's yours. And that will be your homework assignment, deriving the formula. So I'm going to show you how to do this today, but you have to be able to do it on your own on a blank piece of paper. All right, so this is a very useful formula, and it should go onto your formula sheet. Okay, and do not use reference tables until I say so. Now, what we need to do is we're going to derive two useful equations, and I'm going to actually go to the next slide. Are there any questions before we move on? You know what this means in the, like, if somebody does this in Bulgaria, I was told this means yes. So no questions, right? No questions. No questions. Okay, all right, let's move on. What's the formula called? Okay, we got a question. It's just called displacement formula. Let me actually type it here. Excellent question, by the way. Displacement formula. And actually, let me actually make it even more like descriptive. Total displacement formula. But sometimes you can call it average velocity formula, because if you solve for average velocity, how do you spell average? Velocity formula, like that. So if you solve it for average velocity, then you get definition of average velocity. And I forgot one thing. Let me just make a small correction. Now this goes on the video, so it will be corrected there as well. So this is going to be total time, total amount of time. Okay, so we're going to go on to the next slide now. Okay, next slide. So now we will need to, actually, you know what? Let me go back. I forgot something. No, never mind. Okay, acceleration, the word acceleration. So let me write this down. Acceleration, right? A long time ago, people used to say step on the accelerator. Like now it's called gas, right? Gas pedal. Gasoline is gas. Gas laws is gas. When you step on the accelerator, that's also gas. It's like all gas. So, but we're going to be using the word acceleration. We're not going to be using the word gas. Acceleration is composed, it's like origination is two words. Air, I think it comes from some word, I don't remember, I don't know. And then next one is celerity. Celerity. Anybody know what celerity means by chance? Yeah, speed or fast. Right. So so this will be additional and this will be speed. So usually people understand acceleration as like you gain speed, you go faster. We're gonna accept a more general definition. Acceleration could be like when you're going faster, when you're going slower, or when you're turning. That's also acceleration. So definition of acceleration is, let's see, acceleration is equal to the change in velocity over change in time. Or we can write delta V over delta T. Another important thing is that over time we get tired of writing T final minus T initial, T final minus T initial, and we switch to delta T. Gradually we'll switch to just T. This is happening because we are lazy, and smart people are even more lazy. And that's why, like, all those formulas, they take up less space, because you don't want to write lots of symbols all the time. You want to be concise. So for a little while I'll be using delta T, and a little bit later we're going to just switch to T. Why can we do this? So why we do this is because we're lazy, but why can we do this is the reason. The reason for this is that T initial can be always set to 0. You can always reset your stopwatch to 0, right? And then start, time again. So this is the reason why we can do this. This is legal to do that. All right, so this is the acceleration formula, and the formula we had before. Let me just copy that. V final plus V initial times T final minus T initial. And I said I was lazy, but I forgot. So I'm gonna do it again. Oh yeah. Plus V initial times delta T. There you go. Let me actually remove this one. So this way it'll be more consistent. Okay, there you go. So we have a system of two equations from where we want to derive two specific equations. One of them will be D as a function of, all of you are familiar with function, right? What like function is. So this will be a function of V initial, acceleration, and delta T. So this will be, let's call it F1, function 1. And then D, the second one will be, excuse me, another function, which will be the function of V initial, V final, and acceleration, but no time. Who's bothering me? Why does V final not work for displacement? No, it's not. It won't. Okay, who is this? Dayun. So, what do you mean by that? I don't quite understand the question. You can turn the mic.
Yeah, for acceleration you put V final minus V initial, but for displacement you put V final plus V initial for all of your equations.
Say it again. I missed that.
For acceleration, you put V final minus V initial, but for displacement, you put V final plus V initial.
Okay, now I understand what you're saying. Okay, so acceleration is how much the velocity has changed over time. The change is final minus initial. So let's say you were going at 30 miles per hour, and then a minute later, you're going at 60 miles per hour, right? By how much did your speed change? Does that make sense? Your speed changed by 30 miles per hour, right?
Yes.
From 30 to 60. But if I ask you what's your average speed, then if conditions are right, you can say 30 and 60 plus divide by 2, that's 45. So a definition of acceleration is it's a change of velocity. That's why we have delta, change in velocity over change of time. Makes more sense?
Yes.
Okay. All right. So let's try it. So here I'm going to derive this. And usually in class, we have more time, and I ask students to derive on their own. They wrestle and finally derive. Your homework assignment will be to derive it on a blank piece of paper from your head. If you don't remember, you can look it up. You can look how it's done, watch the video, but then try again without watching it. Okay. So for the first one, we need to eliminate v final. So from the equation here, right? I want to eliminate v final. So let me rewrite this thing here. So I'm going to write it up here. Acceleration equals v v final minus v initial over delta t, right? We don't want to write t final times. And then we solve it, it becomes v final equals v initial plus a delta t. Now, if you're not sure how to do it, use algebra, recall algebra, and come on. I'm not going to derive every single steps that usually people do in elementary school or like middle school. So multiply both sides by delta t, and then add the initial on both sides. So it's kind of tough. But we arrive to this. So now we need to replace v final in the displacement equation with this expression. So I'm going to actually point at that. So this way you know where everything goes. So this is going to be replacing, this. No, I went the right way. Go away. This. Okay, so let's do that. D equals 1/2 v initial plus a delta t plus v initial close delta t. Like that, right? Now what we're going to do, we're going to distribute 1/2, distribute delta t, combine like terms, and we will arrive to this. It's supposed to be 2. A delta t squared. So this is a special formula. It's useful, but it doesn't work all the time. Only in specific cases. So, but you will have to know how to derive it, and we're going to use it in solving some specific problems. Okay, so this is our first one. Now we're going to try to get the second one. In the second equation, we want to eliminate time. So then again, I'm going to write this down. Acceleration is equal to v final minus v initial over delta t. So we just swap a and delta t, and we arrive to delta t equals to v final minus v initial over a. Again, if you're not comfortable with this, you think you should multiply both sides by delta t, then divide both sides by a, you can do so. But like I do this in one step, just swap these two and you're done. Now we're going to delta t is going to be replaced here with this. So I'm going to draw another arrow. Let's see, we're gonna draw another arrow. Like this. So I'll post these slides and other slides. I think it looks better on other slides in terms of arrows, but this is like a more open design, so to speak. So let's write it down. D equals what do we have? We have 1/2 V initial or final, doesn't matter, plus V initial times V final minus V initial over A. Okay. Now this could be it, but look, we could probably make it more concise, right? What do we see here? What kind of thing is this? Participation, participation, participation. Looks like quadratic, right? It has a special name, the identity. Does anybody know? Difference of the two squares. They're also called conjugates. Yes, conjugate pair. So that creates difference of the two squares. Excellent. So that's what we're going to use. So I'm going to write here D equals 2 V final squared. Yes, I see that. V initial squared. And over 2A. So 2 and A are both in denominator, so we can actually put them together. All right. And then we're going to box this thing. Box. All right. So those are the two useful formulas that will also go onto your formula sheet, and you will gradually memorize them. I would say like more like get used to them. Okay, you will be able to recognize them and then pull them out of your memory whenever you need them. Okay, so let me look at the schedule. I'm gonna stop the video. How do I stop the video?